Hi, welcome back to Geometry. We're still in Chapter 7. This is Section 7.4, Similarity in Right Triangles. So we've discussed similarity in polygons and in triangles, but these are specifically right triangles in this section. So our objective is to find and use relationships in similar right triangles. It's essential that you understand that when you draw the altitude, remember the altitude is that line that's just perpendicular. When you draw the altitude to the hypotenuse of a right triangle, you form three pairs of similar right triangles. So we're going to explore that in this section. So if you look here at this diagram on this video, this is the altitude. It's perpendicular to the hypotenuse, so it forms a right angle, which then in turn makes you have the larger right triangle, CAB, but then you have two smaller ones. After you've drawn the altitude, you have this pink one, right, DCA, and the yellow one, DAB. So please fill in your note template. You may want to use colors on this. The most confusing part of this is separating the right triangles and turning them the right way. So Theorem 7.3, the altitude to the hypotenuse of a right triangle divides the triangle into two triangles that are similar to the original triangle and to each other. So you would want to draw this picture. The first thing that you would want to draw here is triangle ABC. So that's this bigger one. If triangle ABC is a right triangle, so let's get the right angle, and CD is the altitude. So again, remember altitude is a straight segment that tells how tall a triangle is. And it's perpendicular to the hypotenuse. So that's the altitude right there. Then it forms three triangles. We have this smaller triangle here, ACD. So that's this one. And then we have this medium-sized triangle here, CBD. Tomorrow in class we're going to do an activity where we separate triangles so that you'll be able to visualize this better. But you should really draw them out this way. So if ABC is a right triangle with a right angle at angle ACB and CD is the altitude to the hypotenuse, then all three of these triangles, the initial one, the big triangle that we had, ABC, is similar to this one, ACD, and this other triangle, CBD. And therefore, all the pairs are similar to each other. The big one, ABC, is similar to the smaller one and to the medium-sized one, and they are similar to each other. These are similar to each other. Identifying similar triangles. So this is a difficult task. What similarity statement can you write relating the three triangles in the diagram? An important skill, and you guys hear me talk about it in class, is to be able to draw the triangles separate. So let's begin with this first one. I'm going to look at this one. Triangle XYZ. So in a right triangle you have your right angle and then you have your hypotenuse. So it's always good to keep track of those when you're trying to set your right triangle straight. Then our next triangle that we have is this one, because this is our altitude, YWZ. So I'm going to take it out and I'm going to flip it around. I have YWZ, where W is the right angle and YZ is the hypotenuse. So I'm facing it in the same direction. Now I have this smaller triangle here. I went from the small side, X, to the right angle, W, up the hypotenuse, Y. So X, W, Y. Where that's my right angle, and this is my hypotenuse. So the similarity statement that I could write here is this. Triangle. Again, you want to develop a system that's going to work for you. I'm going to go down this short side, across the long leg, and up the hypotenuse. So X, Y, Z is similar to triangle. I'm going to name this the same way. Y, W, Z. And then my third triangle, I'm going to name it the same way. Similar to triangle, going to go from X to W to Y. X, W, Y. We've already kind of talked about this in class. You did the puzzle after the quiz the other day. Proportions in which the means are equal occur frequently in geometry. For any two positive numbers, A and B, the geometric mean of A and B is the positive number X, such that this. I gave you a more basic definition the other day of geometric mean. It's the square root of the product of the two numbers. So when I cross multiply here using the cross product property, right, I'm going to get X squared is equal to A times B. Another way to look at this is X equals the square root of A times B. So finding geometric mean, well, what's the geometric mean of 6 and 15? I want to find the product of them. So 6 over X is equal to X over 15. Now you can't cross reduce here. You're not multiplying fractions, you're solving a proportion. So using the cross product property, I'm going to know that X times X is X squared is equal to 6 times 15. That's the product, 6 times 15. Now you can calculate 6 times 15, but then you're only going to have to factor out your perfect squares. Really, X squared is equal to 6 times 15, so that means that X is equal to, when you move squared to the other side of an equation, the opposite of squared is square root. So it's the square root of 6 times 15. Well, I want to take out my perfect squares. We've done this in Algebra 2. The factors of 6, that's 2 times 3. The factors of 15, that's 3 times 5. A pair is a square. I have a pair inside of this radical. I have a pair of 3's. So X is going to equal, a pair can come out as 1, so it's 3. Inside that radical, I still have 2 and 5. 2 times 5 is 10. So I simplified this radical. And again, you could have done 6 times 15 and gotten 90. And then the factors of 90 are 9 times 10. And the square root of 9 is 3. But why multiply to only divide, to factor it out? So this might be an easier method. The corollary, remember corollary means something you can easily prove. It's like the attachment to it. The first corollary that we have to Theorem 7.3. The length of the altitude to the hypotenuse of a right triangle is the geometric mean of the lengths of the segments of the hypotenuse. So, in this example, you definitely want to use colors, you definitely want to draw these pictures. So in this example, we have this right triangle. And because 4 is the altitude, so we have this right triangle here where 2 and 8, this is 2, this is 8, and 4 is the altitude. So, just like we did a few minutes ago, you could separate these triangles into smaller triangles. I have this small one here that has a side of 4 and a leg of 2. I don't know what the hypotenuse is. And then I have this larger right triangle. But I'm not going to use those pieces. I'm going to use this smaller, the medium-sized one that's here. So I'm using these 2 triangles that are within this one. And it has a side of 8. And then that smaller leg there is 4. And I don't know the hypotenuse, right? Because this is the hypotenuse, this is the hypotenuse. So, 2 corresponds to 4. So 2 over 4 is equal to 4 over 8. When you use the cross product property, they're equal. So we can use this, the geometric mean, in order to find the length of missing pieces of a right triangle. The second corollary that we have is that the altitude to the hypotenuse of a right triangle separates the hypotenuse so that the length of each leg of the triangle is the geometric mean of the length of the hypotenuse and the length of the segment of the hypotenuse adjacent to the leg. So, simply stated is this. This piece of this big triangle, if we're looking at the if, AB corresponds to AC in this smaller triangle. Again, it's difficult to see the triangle. So in this example, I am using the larger triangle. So my hypotenuse is AB. My leg here is AC. And I'm also going to use the medium-sized triangle here. So D is my hypotenuse. My right angle, sorry. And I have my legs here. I have BD that corresponds to BC and C. So our ratios, AB over AC corresponds to AC over AD in this smaller one. And for the second ratio, AB corresponds to CB and CB corresponds to DB. So the real life example is down here below. Again, the most complicated thing about these is separating these triangles, which we are going to practice in class tomorrow. So if you look at this example, you're using this little tiny triangle and you're using the larger triangle. So hypotenuse over hypotenuse is equal to leg over leg, or hypotenuse over leg equals hypotenuse over leg, depending on how you do it. Let's try some. It might be easier that way. So, what are the values of x and y when we use algebra? We want to draw these triangles separate. And again, you want to make sure that you are doing that. You have this larger triangle here. In this bigger triangle, I know that the base leg is x, and the hypotenuse is 4 and 12, so it's 16. And this is my right angle. Then we have 2 smaller triangles on the inside. So let's separate them first. I'm going to go in order, so I'll do the medium one next, the middle one. So I have this middle triangle. So I know that the smaller side is y, and I know the longer leg is 12. I don't know the hypotenuse. The hypotenuse is the side across from the right angle. I don't know it. So we don't have that information. And then the last triangle that we have is the small one. And again, you should be separating these with me. It's this one here. This tiny one, where I know the short leg is 4, and I know the hypotenuse, because that's the side across from the right angle, is x. So this is a 4. So now I can write ratios in order to solve for x and y. I need to find matches. So if I look at the blue triangle and the purple triangle that I've drawn here, I can write a ratio of the sides. The hypotenuse of the blue triangle, which is 16, over the hypotenuse of the purple triangle, which is x, is equal to the short leg of the blue triangle, which is x, over the short leg of the purple triangle, which is 4. Now I can use the cross product property in order to solve for x. So this is geometric mean, because when I cross multiply, x times x is x squared, is equal to 16 times 4. Now you can multiply 16 times 4 and get 64. And you know the square root of 64 is 8. So x squared equals 64. So x equals 8. But you could have also moved that squared to the other side and said x is equal to the square root of 16 and 4. Square root of 16 is 4. Square root of 4 is 2. So that's 8. Either way, you're going to get 8. If you'd like to see the work for this one again, please rewind this. Otherwise, I'm going to erase it now so that we can solve for y. So the long leg of this smaller purple triangle is y. So this side is y. This is 4. So now I'm going to use the red triangle, which was the medium-sized one, and the purple triangle. So 12, which is the long leg of the red, over y, which is the long leg of the purple, is equal to the short leg of the red, which is y, over the short leg of the purple, which is 4. Again, using the cross product property, I'm going to find the geometric mean, because y times y is y squared. So when I cross multiply, y times y is y squared is equal to 12 times 4. I know that 12 times 4 is 48, so I can find the square root of 48. It's not a perfect square, so I am going to have to factor that radical. I'm going to have to simplify it. Or I could just do this. Y is equal to, I could move squared to the other side of my equation, square root of 12 times 4. Well, I know that 12 is 4 times 3, and then I have this other 4. So I have 2 4s in there. A square is a pair, so 2 4s, 1 4 comes out. So y is equal to 4 square root of 3. Or if you had the square root of 48, right, you know the factors of 48, square root of 48, I could have said that I know that that's 16 times 3. And then the square root of 16 is 4, and that'll leave me 3 behind. Either way, y is 4 square root of 3, and we already solved that x is 8. So x is 8, and y is 4 square root of 3. You try the next one. See if you can figure it out. See if you can solve the proportions. See if you can draw the triangles out. Pause the video. See if you can do it. And I'll put the work up for you. So you should have drawn the 3 triangles separate. I have this larger triangle that has a right angle with a hypotenuse of 9 and a short leg of x. Then I have the medium-sized triangle. That one has a short leg of y and a long leg of 5. And then I have the smaller triangle of the three that has a short leg of 4, a long leg of y, and a hypotenuse of x. So the proportion that you could write to solve for x, I would use the blue triangle and the purple triangle. And I would say hypotenuse over hypotenuse equals short leg over short leg. So I would cross multiply and get that x squared is equal to 36. And therefore I know that x is 6 because the square root of 36 is 6. For y, I would use the red triangle and the purple triangle because they both had y. And I would say long leg over long leg equals short leg over short leg. Cross multiply. So y squared is equal to 20 because 5 times 4 is 20. Or you could have said 5 times 4. So y is equal to the square root of 20, which is 5 times 4, and the square root of 4, right? This is 4 times 5. 20 is 4 times 5. You could have just done that from the beginning. You didn't have to multiply them. So y is 2 square root of 5 when you simplify the radical. So now we found x and we found y. All right, last example on today's notes. Finding a distance using a real-life situation. You are preparing for a robotics competition using the setup shown here. Points A, B, and C are located so that AB is 20 inches. And AB is perpendicular to BC. Because you know the perpendicular, you know that's a right angle because perpendicular lines form right angles. Point D is located on AC. So that BD is perpendicular to AC. Perpendicular means it forms right angles. And DC is 9. You program the robot to move from A to D. So this robot's going to go from here to here and pick up a plastic bottle at D. How far does the robot travel from A to D? So this would be a real-life application of geometric mean using similar right triangles. We would do it the same way that we just did the last two problems. You want to identify the triangles that you're going to be using in order to find x. So what you want to do is identify the triangles that both contain x. So in this situation, the triangles that both contain x are the larger right triangle, this one here. I have angle B, which is the right angle. Always want to focus on that. And I know that AC is the hypotenuse. AC is the hypotenuse. D is along this line here. If I know this piece is x and this piece is 9, then AC, the hypotenuse, is represented by the expression x and 9, x plus 9. AB is 20 inches long. Then I want to use the medium-sized triangle because it has two measures. I know I'm not going to use the small one. It only has the 9. It doesn't have anything else, and it doesn't involve the letter x. So I have this smaller triangle. Now, I need to recognize where my right angle is. It's at D. And I need to recognize that my hypotenuse is AB. My hypotenuse is 20 inches. A to D is x. So now I can write a proportion that I can use to solve for x. You ready? Remember your algebra too. So, hypotenuse over hypotenuse equals long leg over long leg is what I'm going to write here. This is my hypotenuse 1. This is my hypotenuse 2. This is my long leg 1. This is my long leg 2. Okay? Because this is my first triangle. This is my second triangle. So I am going to put hypotenuse 1, x plus 9, over hypotenuse 2, which is 20. It is equal to long leg 1, 20, over long leg 2, x. Now we're going to use the cross product property. What's going to happen when you multiply x times x plus 9 is equal to 20 times 20, or 20 squared. So I'm going to get x times x is x squared. X times 9 is 9x, is equal to 20 times 20 equals 400. This is an equation because it's got an equal sign in it, and it's got an exponent raised to the power of 2. So it's a quadratic. You use the zero product property to solve a quadratic. X squared plus 9x minus 400 equals 0. To factor a quadratic, it has to equal 0. I want to find the factors of 400 that have a difference of positive 9. X times x is going to give me x squared, and 25 times 16 is 400. 25 minus 16 is 9. So x plus 25 equals 0, and x minus 16 equals 0. So x is negative 25, and x is 16. So we're looking for a distance that this robot's going to travel. Can the robot travel a negative distance? So this one is not a solution, right? You have to have a positive solution. That's an extraneous solution. It doesn't work. It doesn't make sense. So the robot's going to travel 16. 16 what? It's in inches. The robot's going to travel 16 inches. We will practice this some more tomorrow in class.